Hello everyone. I welcome you all to this video wherein we will now start the code for the dynamic range sum queries problem. Alright. As we have already seen the theory, so let us start with the implementation of the square root decomposition algorithm. I know that this is going to be the very first problem that we are going to solve using this technique. So I will go slowly over the code so that everyone understands what we are doing over here. So very first thing is, let us look at what is the input format. So the first line has two integers n and q. So let us define over here what n and q are. So let me take n and q, right? So let us take the input. Now we have taken the input. After that, second line has n integers, so we have to define n vector, uh, wherein we can say take all the integers. So int I equal to 0, I less than n, I plus plus. Let me take input. So over here, over here we have taken the input from the user, and now next part is, okay, so this will be of size n. All right, so the next part is, there will be q queries. All right, so now before we start answering queries, what we have to do is we have to do quite a few things. All right, and this will be initializing what, as I said, as we discussed over here. First thing first, that we have to find out what is block size and the number of blocks. So what will be the block size? We ultimately concluded that we will take the block size as root n. Alright, so let us say that the block size will be nothing but square root of n. Alright, and what will be the number of blocks? So number of blocks will be nothing but ceiling of n divided by block size. So instead of this, let me, for safety, because both of them will be integers, let me add 0.0. Okay, so before proceeding forward, let me just print out what is the uh, number of blocks. And oh, sorry, so that you get clarity, right? So before we move forward, let's do that. So I will quickly give you the input from the example itself, which will be something like this. Because we have not taken input for the query, I will not be giving that, right? So what is the expected output? I don't have any expected output right now. So let's run this program and see what happens, right? So we see that the number of blocks is nothing but 4, and this is consistent enough with what we designed over here. There will be 4 blocks because 0, 1, 2, 3, we understood that root n will be 2 and 8 divided by 2 will be 4. So what if I increase this to 9? Okay, because we know that square root of n, which is 9, is 3, right? So if I do that, then the square root n will be 3, and let me make it to 10 for us to understand better. So why I am doing this is, if my n is equal to 10, my square root of n will be 3, and the number of blocks should still be 4, right? And in this particular case, let me add two more numbers. So now number of blocks should still be 4. Yes, and each block will have size 3, and each block will have size 3, but there is a flaw in this, and the flaw is, if you look at this input, then this input will be something like this, and the blocks will be made something like this: 3 2 4 5 1 1 5 3 2, and last block will only have one element. It will not have other elements, right? So each block size will be 3, but last block is a special case wherein the block it will only have the it will only have elements less than or equal to 3. Okay, so this is understood, and now let us move forward in our question. So once we have done this, okay, so once we have done this, now the point is that what is the need of making these blocks? So like what are we going to do with these blocks? So as we understood from the question that for each block we need to store one thing, and that thing is nothing but the block sum. And over here, if you remember, PBS denoted previous block sum and NBS denoted next block sum, which mean that for each block we need to store what is the sum of elements present in that block. Okay, so let me bring this again, right? So if I say that this is 3 2 4 in one block, 5 1 1 in one block, 5 3 2 in another block, and last block will have 1. So the block sum will be over here 9, will be over here 7, will be over here 10, and will be over here 1. So ultimately we want a vector of int, and the int is, and it can be block sum, and it should have size nothing but equal to the number of blocks. All right, and now how do I get to know this sum? All right, so this is easy. What we can do is, first of all, we have to iterate over all the elements present in the array. All right, and what we can do is, let's initialize the block sum for each block as 0. All right, so the important part is that which will be helpful for us in the subsequent queries, a part of code as well, that if I give you an array index, so if I tell you that randomly say that okay, this is the element, this is the index in the array, then I need to find out that in which block this particular index is lying, right? So for this index I, if I can find out what is the block index. Okay, so I'm defining a variable here which is block index, which simply means that which block this particular index is lying. So if I calculate, then it will be 0 1 2 3 4. If I am talking about I equal to 4, then my output should be that your block index vi should be, if I know that 1 is nothing but coming over here in second block, so its index should be 1. All right, so how do I compute that? So computing that, I will do nothing but I divide by how many uh, elements are present in each block. It will be block size. Okay, so if you quickly note over here, in my case n is 10, so my block size will be nothing but each block is having 3 elements, so my I is 4, so 4 divided by 3 will be 1, so my block index is 1. If my I is 6, then each block is having 3 elements, so 6 divided by 3 will be 2, so my block index will shift to this. If you look at this 5, then the index of this 5 is 6. This is 0 1 2, this is 3 4 5, and this is 6. So this is a perfect block index. So what I will do is, the block sum is nothing but what I will have to do now is, just for this block index, just update the sum by adding this particular value, which is nothing but array of I. So using this, I can simply add, okay, let's not erase things. So using this, I can simply add these block sum. So now for my clarity, let's have uh, let's print the block sum. I know that output should come like this, 9 7 10 1, but still let us look at the block sum. And you can see that the block sum is 9 7 10 1. So uh, we have completed the block sum. So now we are in a very good position to start querying or start answering each query. So now let's come over here again. The second line we have taken this input. There will be q lines of query. So let's start with query. Now there will be two queries. One, the first integer will be 1 or 2. So let's say int type. If type is equal to 1, then we will do something, else we will do something. So if type is equal to 1, then we mean to say that update the value at position k to u. Okay, so we have to take k and u. So the position is k, but this is 1 based indexing, so we need 0 based indexing. Okay, so what we are going to do is we are going to say what is the previous value of this position. That will be this. So we store it somewhere in PV variable, and then we update this with the new, which is nothing but u. And now apart from that, if you remember, then we told that for each update query we need to update the block sum as well, right? Because when elements change, the block sum is going to change. So over here this block index is going to help us, right? So this block index will tell me which block will this element is this element lying in which block, and therefore we are going to update the block sum for that particular block, right? So how will we do that? We will say that is nothing but we will subtract uh, so you can see that previous block sum minus the current value, which is nothing but sorry, minus the previous value, and this is the value that we are removing from the block, and this is the value that we are adding into the block. So this is the updated value of the block sum. Okay, so this is what we have to do if that query is of type 1. Now what if the query is of type 2? Okay, so let's talk about that. So if the query is of type 2, then we have to return the sum again. So let me go to this. So in type 2 we will first of all find out the block index BL and BR. Okay, so first of all find out the, let's take the input as what is the range. Okay, and let's do L minus minus and R minus minus because we are following zero based indexing. And now what we have to do is we have to simply calculate the block index BL, which is nothing but L divided by block size, and BR, which is nothing but the R divided by block size. Okay, so now after this BL and BR, after the BL and BR are computed, we can simply say that the answer for, we can declare the answer as 0 for this particular query. Alright, and for all the elements, for all the blocks starting from BL plus 1 to BR minus 1, int I equal to BL plus 1 up to I less than BR I plus plus, we can simply add the answers of those block, as we have already seen over here that each block is either not included or included completely or included partially. So BL plus 1 to BR minus 1 are included completely, so we do not have to iterate over their elements, we can simply add the answer. Now for block BL and block BR, those are included partially, so we have to iterate over the elements in that array. So now the point is, how do we identify what is the end, like what is the uh, reach, like when we have to stop? So for that what we will do is we know the index, right? We know the index L, and we want to know when this particular block is going to end. So we already know that each block is having, we know that each block is only having block size number of elements, right? So if you look at carefully, then we can know if I am at a particular block, let's say I'm at block number 0, this is block number 1. So block number 1, so if I say uh, each block is having block size number of elements, then we can simply say that the end of, if I am at the ith block, okay, then the end of ith block will be nothing but I plus 1 into block size. Let's verify that. So if I am saying that I am at the end of first block, this is zero based indexing. So if I say that I is equal to 1, then we will simply say how many elements are going to have. I is 1, so 1 plus 1 is 2. 2 into block size is 3, 6. So we will have 6 elements by the end of this. So what will be the index of the last element in this block? It will be that. It will be this, right? So by using this similar technique, what we are going to do is, what we are going to say, what is the last uh, index for the block BL. So it will be nothing but, what is the block index over here? BL. Similarly, int, what is the last index for BR? It will be nothing but, what is the block index over here? BR. Okay, so this is simple. And now we know what is the end, like, but we need the first index for the BR, right? Because for BR we are going to start from here, and we are going to start from here and end at the given index, that is R. So what will be the index, first index of the block BR? So it will be nothing but this minus the block size, okay? Or we can say, if I optimize it, then blocks, this will be nothing but BR into, like, this will be nothing but simply this, and so let's BR into block size basically. So let's come over here and understand. So I want to find out that if I am at the ith block, then what is the starting index of this block. So I know that like previously we can use this to calculate the ending index of the last block. So ending index of the last block will be I minus 1 plus 1, which will be I, into block size, right, minus 1, and this is the ending index of the last I minus 1 block. So the starting index of the next block will be plus 1. So just remove this 2, and therefore we will get this. To verify that, if I want to say that I am at the I equal to 1 following zero based indexing, I am at this block, then 1 into, what is the block size? Block size is 3, so 1 into 3 is 3. The index of 5 is 3 because we are following zero based indexing, right? So this simply becomes this. This is the first index for BR. So now to add to the answer, we will simply say for int I is equal to, starting from L, we have to go until last index of BL and I plus plus, and simply say answer plus is equal to A of I. And similarly, starting from I equal to the first index in the last block, and then I is less than equal to R and I plus plus, and simply we will update this with our answer, and finally we will see out answer, right? So I hope you understood this, and let me quickly run through the sample cases. The sample test is this. So the output is 14 4 11, and oh the output should be 14 2 11. So we made a mistake somewhere. Let me check. Okay, as you can see that the first two queries are, we are not making any kind of update. All right, so uh, the last query is being told after the update, so there is some problem when in the initial phase, like in this particular part there is some problem, but this particular part is not having any problem. Okay, so what is the problem in this particular part? Let's dry run it. So int lr, we took the input, then we decreased it because this is going to be a zero based indexing. So we are going to add this to 1, right? And then we get the block sizes. So these two one completely lie in this particular block. All right. Okay, so these two blocks are same. BL and BR are the same. So in this case, this for loop will not be included, right? And then if this block are the same, like okay, now the problem that we found is that if both the elements are present in the same block, let me draw it over here, that in the sample input uh, there will be a block over here, there will be a block over here, right? Or maybe not, because over here n is 8, so square root of n will be 2, so each block will have two elements. Okay, so now the problem is when both these elements are present in the same block. So if BL is equal to BR, then we can simply say that compute the result for that block by iterating it. That is the best possible case, like we are answering it in order of root n time. Alright, so mm, so if BL is equal to BR, then we do not have to make this count. Like we are adding the answer twice. So or we can simply add one line that if BL is not equal to BR, which means that these blocks are different, then only add the answer. That this will make sure that the answers are not added twice. So if I run this now, you will see that it's 14 to 11. Alright, so instead what we can now try is we can submit this code on CSCS and verify whether it is okay. So I have to log in, and what we can do is we can submit this, and let's submit this. Okay, so there is something wrong, and I think yes, the problem is actually over here, that if let us say that we are in there like PL and BR belongs to the same block, and let us say that this is the block, and we are having certain element, we have then L, then we have certain element, then we have the R, and this goes on. So in this particular case, if BL is equal to BR, then we just need to compute L to R, right? So in this case, what we do is let us write it over here itself. If BL is equal to BR, we define the answer over here, and if BL is equal to BR, then we can simply without doing anything, we can say let's start from L and go to R and calculate the answer and see out the answer, right? If BL is equal to BR, if they are in the same block, then just calculate the answer, because we know that it will take less than order of root n time to answer that particular query. So else we have to do all these things. And this condition now is not required because we know that BL is not equal to BR. Okay, so now I think if I submit this now, it should be good. And the second thing is the value that we are dealing with, right? So it should be int should be converted to long. So let me define, and everything, let's convert it to long. Okay, so now if I submit this, it should pass the second test as well. Okay, so with this we completed this problem, and we will study more in detail about square root decomposition and its applications. There is still some theory left, and then we will move forward with more complex problems in this domain. So thank you for watching this implementation, and look forward to see you in the next video.